Okay, so we have here our mlen, and if len is larger than mlen, then we return 1, and if it is smaller, then we return -1, and if it is equals, then we continue to the next check. So now we have here the next check, and again, if this is, which one we started with? We started with the other one. So if this character is bigger than that character, then return 1. Else, if it's smaller, return -1. And if everything is the same, then return 0. And as you see here, we check with the compares, return 0. And this is more or less how most string comparison functions are implemented, since we would like the ability to sort strings in a deterministic way. We just sort them by characters. How we sort them by whether even we sort them by length is a different story. That actually in our case would not necessarily be required, because at some point one of the strings will contain null, and then the other one not, and then the whole thing will just break out. So in theory we could actually even simplify this and not do this comparison. It's maybe actually a good idea. Then we don't even need the x length for this. We can just leave it like this, and it will still work, because we assume, of course, that both strings are allocated. But as soon as we reach a situation where one would be 0 and the other isn't, then we already break out of the loop. So we don't actually need to waste cycles on checking the length up front. We can just go in directly. And this length checking, if we use xlen, then of course it is slow. If we would be using just comparing directly the cached values, then it would be faster. So what we should probably do, actually we should leave this in, and later rework the code such that here it will take not a C string but an actual CX string. As you have also maybe noticed while we were writing the code, even though at some point were some minor bugs, nothing was underlined, and this is another limitation of templates, that the compiler, the IDE does not do that much of preliminary evaluation of the code, because it kind of doesn't know yet which types you will use it with. So you have less help when writing this sort of templates yourself. You need to write the right code, then try to compile it, and then see whether it compiles. Of course, once it compiles, then it does all the required checks. So we can now create a string of type. Actually, we probably don't need to provide a type. We can just assume that it will be smart enough to figure it out. A string. Oops. Blah. Is it smart enough? It's not. Okay, then we tell it that we want a char. And then we will create another one with vchart underscore, and we will call it vstring. And both should work, each of them for their own. We cannot compare one to the other. Oops. If this thing is equals that thing, even if it's even though it is the same class, as you see, the compare doesn't work. And the reason behind this is because effectively what the compiler did, as I explained with the xlen function, it creates an entire copy of the whole code, changes the name in a way that makes it unique, and reflects which type this thing uses. So it's like if we would try to compare two different types to each other. So this will not work in this way. Now, that said, there would be ways how we could implement at least some subset of the functionality, but that we might do that later. So just to explain how this would be, how you would do something if you want a template class to be more useful with some existing types. Okay, I see here I have a few more typos. And as you have seen, the compiler, even they were here, didn't complain because it didn't compile them. Okay, so what you would do if you would want to have at least some functionality shared or some ability to do something with two different implementations of one template, you could derive both templates from the same parent class, and then if you want to do some operations with them, all the operations which the parent class supports, those you could do on the two incompatible types. So for example, if we will really want to just compare them, we could implement this functionality. There is a important limitation, namely the parent class from which we derive it obviously in this case should not be a template from some type. You can of course derive from another class which is another template class, but then of course you again specialize this thing, so you cannot use it for this sort of abstraction. And if we would want this comparison operator to work like one level higher, then we would need to devise a way how we can make a comparison without knowing which type will be used in the potential implemented subclasses. And one actually maybe we should implement this because this is a good exercise in doing such things. So to be able to implement basically our compare function in a way that is agnostic to the type, we would need to define a type or a way to access in some way the type which we have there in some way that will be agnostic to the actual type. So we can, for example, create a protected function. So let's start with implementing the parent class. So cx string base. This will be just the class public string base. Public equals string base. So we just have a constructor, and we want a destructor just to be on the safe side. But we don't want to do anything in it. And this thing will be an abstract class, so it will contain functions which don't have any actual implementation. So we want a, let's say, void, no, bol, get char at function. So we want to get a character at a position, and the return type is boolean because if there is no character at the position, it will return false. So if we try to access an empty string or an invalid offset, we want to return an error. So we will start at some point to make this class also like error fault tolerant. So the current implementation is here fault tolerant, but here already isn't. So this is something that also will need some work on to make it work correctly. But here we will try to already start. So first of all, we want to provide the offset, so size t position, and then we will want to get our character out, but we don't know how large it will be. So what we do is we make a void asterisk, so pretty much an arbitrary type, and what we will later pass to this function will be a pointer to memory which we would assume is large enough. Or actually we can even make this one better, since the memory is already allocated. We can make this a pointer to a pointer. That's even more fancy. P char, and then we made another size t asterisk p u size. So we have a pointer to a pointer which will get the memory address of the next character, and we will get the size of the character returned. But since we don't know anything about the implementation at this point, we just make this a virtual function. So this function at this level doesn't exist, but other functions within the CX string base can use this function, and this function needs to be implemented on the CX string, which we'll do later. And now we grab some of the operators which we could conceivably implement using getChar in a reasonable way. We grab the compare function, this one, as well. And since we will want to make this more performant, we will add here another helper function, size t len is fine, which will return the length of our string. And that's that. So here we need, of course, to change a few things. Compare. Now we said this thing will take a base class, basically. Right, this for now I will just replace with true and say it's a to-do. Compare should be fine. Why isn't it? Because compare isn't const. Compare must be const. Oh, that's a bug. Well, not anymore. We have removed it from here. It was a bug which we didn't run into because I said the compiler only compiles the actual functions which we actually use. Since we didn't use the equals equals operator in the code, it didn't run into the bug that I have forgot to make compare const while using it here. But now it should not longer complain. Why is it still complaining? Return no, I think I fixed that. It is just complaining about something else at some point. Let's just copy const string base const. That should be fine now. We'll just ignore the error and then continue later. So since we have a C string, we can just access its did I make this private? No, it's protected. We cannot access it. We should use of course we should use here strlen. That's why I added okay, we have I didn't define len. That's a thing to remember that everything you want to use in your parent class, you need to of course define first. So size is also virtual, suppose null. And this one should be const as well, just for good measure. But isn't this compare is here and both are const? I have no idea why this is complaining. Not modifiable. Wait, white must very bad error. That's of course must be a double. It helps to read the error messages instead of just trying to spot what's wrong with the code, because sometimes you might be blind to an easy mistake like forgetting an equal sign, which is a pretty bad mistake actually. Okay, so what we do is here we cannot access almost anything of our other function, but we can use those things. So yeah, okay, and now the funny part, how to get apparently I forgot those to close. How we will handle, okay, here we also need that behavior. Actually we don't need this. This is kind of implicit, so let's save code because we used the name. It's usually a good idea to use longer function names, longer variable and function names, because then we will not run into name collisions too easily. So what we now need basically is we need a pointer to the first character. So void stern p char left char right. We can we don't need to. We can as equals null, and then we will need the length, so that's size t. Len l is equals len r. Okay, and now so we have already checked that the lengths are the same. So actually we don't assume that it will ever fail, so let's don't waste CPU cycles on initialization. Just directly go to get char. On the one thing, position is I. Pchar is a reference to our lchar case size is reference to our len_r, and then we do the same with the other star punkt, and now we say this one was the R version. Okay, so what we already know is that those two characters, how to say it, they might have different lengths, so we need to check this first. Or what we could also do is we could so there are two strategies. One is that we just say if they are not the same length already, then we fail the comparison. But then if you would have kind of the in quotation same string, like the same text within our white string and with our normal ASCII string, then we would have failed the comparison, which we don't want to. So what we will do is we will require up to the length of the shorter character, the character value to be the same, and the rest of the values to be null. This will allow us to work well with implementing a easy comparison between ANSI and Unicode strings, which will yield reasonable results when used with strings that don't contain the extended ASCII. They don't actually contain the extended ASCII characters. So we want to have the shortest length. So size t len s is equals so if len l is smaller than len r, then so we are using the trinary operator here, then len l and else the len r. So s will be the shortest, and then we want the longest. So here we change this. If len is larger than r, then it's l, and if it's shorter or equal, then it's r. That's fine. So now we do our first comparison. We can use the memcmp function. Admittedly, just for one character, that's a bit overkill, but since we might have a few characters, let's just go with it. We take the first pointer, we take the second pointer, we take the shorter length, and int ret. And the memCompare will return 0 if they are same. So if it's not 0, then we just return it. And if it is 0, then we proceed with the next check. And now what we want to do is if len s is not equals len r, then we will want to check the rest of the character, whichever of those is longer, whether it really just contains zeros. So how to do that best? We will need a loop for that. For int j is equals ls, comma j is kleiner als l j plus plus. And what we now need here will be a pointer cast to a let's say byte. We don't have byte defined. Let's go with char stern per is equals. Okay, so we will copy this and fix it. So if len l is smaller than len r, then it means that len r is longer, so we'll use the pointer to len r, else we will use the pointer to len l. Is that correct? Yeah, r is bigger than l, then we want this one, else we want the other one. And then of course we need to cast that to char in both, oops, not here, here in both cases. So we have a pointer which will be assigned the pointer to either one of those strings, whichever has the longer character type. And now we will check starting and at the numeric index j whether this is null. So if this is not null, then we break out of that return, and then we will use this here to return either -101 sorry, or 1. Yep. Okay, so this way we have a somewhat within reason type agnostic approach, which allows us to compare those what is it almost strings. As you see here, it's complaining because we have not yet implemented the get char add function on the template. So let's do that now. Somewhere here. That doesn't need to be const. That's just a value. Right here. So we have virtual. We don't need to write virtual in the derived class because that's kind of inherited anyways. But we need the implementation. So that's pretty easy. If m and m data and m length is is bigger than position, then we return. Then we don't return. We write is equals reference p data at I and return true, else return false. And we need to assign PU size, which we can always do. Asterisk PU size is equals size of t. We could improve that. We could have a separate function that returns this independently. That sounds like a good improvement. Let's do that. tlen. We just call it tlen. Then we don't really need len still. Or len t, lang of type. Let's call it len t. Yes, and we wanted to change this, not longer requiring this thingy. Where were we? Len this. Len, we will need this. We don't need that. And our len t is super trivial because it just returns size of t. Right, so here it returns the pointer this way. Okay, so since we only have one value that we are returning, we could streamline this to actually just return a pointer. And if the pointer is null, then it means the access was invalid. That is an improvement. And else return null. Okay, then we need just to again adapt this function to do what we want it to do. So here we need those two values. That's equals L was ourself, so len t, and R will be str len t. Right, and this thing can be now directly assigned. Looks nice. So, let me think. Can we somehow improve that further? Well, len s and len s, those will be constant values because they are just computed once based on here, so we can move them out. Yup, this is fine. I mean, this here could be improved, but let's leave it just for the sake of simplicity. And then we have that. Yeah, that's fine. Could be working. And now let's try, and voila, our comparison might work. And f, same or different. Let's see if that works. So we have initialized both strings with blah blah. So it should say that they are same, even though they are different different types. let's see. Okay, we have some error somewhere. Of course, we already had L short, and let's keep that for total S full. Full is better. Short and full up to full, and the other ways we are using length. Okay, that should be fine. Okay, more bugs. Right here, that should be of course position and not I. Strichpunkt. And it printed same. Yoo-hoo! But it complained while building. We had a warning. Because that should be size 10. Size TJ, okay. And now let's make them actually different. Blah x. And then it should say different. And it works. So, as you see, you can in fact make templates work even with each other, even if they have different type, but it is complicated because the one part which makes whatever operation they are supposed to do with each other must be implemented such that it will be completely agnostic to the type with which each of those templates will be implemented. So in our special case here, what we have done is we have provided a function to get the actual character size at the string, to get the string at the relevant position, and sorry, to get the character at the relevant position, and here not actually the character but just the memory address of the character, which the way the system works allows us to access an arbitrarily large amount of memory. And we implemented a nice agnostic function. One very simple fix which what we should do is to change those to use actually the string, since that's more elegant. Let's quickly do that since we already done this here. 1 and 2. Okay, so here length we can just use the len operator, and here we use the typo. We want this to be of course a C string. Then we have more things available over here. Oops. Punkt C string. And with the append it should be similar. So here we use just punkt len string size type, and here we go with that. Yep, so that's the next improvement, and voila, we have implemented a class which can be a wide string, it can be a narrow string, and you can even compare wide and narrow strings to each other, and it works. Okay, so now there is one more thing which I think would be a good homework, and I hope it will not be too complicated. This will be to implement a constructor which will allow us to create a string of, for example, a wide string from a narrow string or vice versa. So what we want here is we want to have an explicit CX string which takes a base string, and that will need to be implemented. okay, let's write a usage example. So we want to create a, so we have, let's go the easy route, a string 2, and we want to create this from a string. So the way this is supposed to work is that it should work by creating a new S. Is this actually renamed? As it's still not renamed, so let's quickly rename that. SX string. This should work by creating a new SX string of the maybe not of, but with the pay data. The source characters are either the command drop the high width. So it will work for if our string basically contains ASCII strings, but if our string would contain Unicode strings and we would cast it to an ANSI string, then it will not work, and this will be a very bonus homework. When converting from from a wide string to a string, convert the which cannot be fed directly to their UTF-8. So this is a bit more sophisticated. So the idea is, normally when you operate with strings, especially when you save data to files, you would not want to save every string in a format which in the worst case would mean that you are using 4 characters to just save 1. So to work around this limitation, different character encoding schemes have been developed. One of them is UTF-8, and what it basically does is for the most characters, it just copies them if it can. But for the wide characters, which would need more than 1 byte to be represented, it will use a special sequence of characters to encode them. So if you have just an ANSI string, it will look in UTF-8 just normally, or you can just directly copy it. But if you have a wide string, you will still be able to represent it as UTF-8. So this is code-wise about a page of code, but a sparse page to convert and to convert back. Yes, and we of course want to convert back. And to Unicode. And let's here be clear that a wide string is a wide Unicode string. This is optional, but it would be a good exercise, I think, so you can do that as well. Right, yo, are there any questions at this point? No questions? Okay. Um, Good. So since we only have about half an hour left, and actually, since we didn't make a break, it's rather more like 20 minutes of spare time. We could take a look into one more funny thing that we can do with our string here. Namely, what we could do is we could implement some, let's say, improved behavior of the string in case when the string gets copied. So as you see from our current string, our assign function, each time we are assigning one string to the other, makes allocates new memory and copies the entire string. If the string is long, this will of course take the right longer amount of time. So if you are passing a string as an argument to a function, of course a trivial thing you can do is just pass it as const reference, the way we already did it here. So this way it's kind of passed as a pointer, and the compiler ensures that you won't alter the data, and this is extremely fast, but of course it is limited to certain use cases, and you can not alter the string in the meantime somewhere else. So it is useful, but it is limited to certain use cases. It does not give you the full flexibility as you would have with a variable. When you assign it, then what you would want is you would want to have your own copy that you can modify and alter at any point in time without having this operation influence the content of the original variable. And there is a strategy, a scheme, how you can achieve such a behavior without at the same time always copying the string. So this mechanics is called copy on write, and the idea is that you do the copying only when your code sees that you want to actually write the string. As long as you don't try to write to the string, it will be a very fast copy where it just copies a single pointer, or maybe a few more very trivial variables. So I think the time which we have left should be enough to implement such a copy on write mechanics for our string. So to do that, one thing we need will be a variable that will be a reference counter. So let's say int and what would we ideally want here would be for this reference counter to work in an atomic way. So this means that we can bunch a set of operations together, and then we have the guarantee that they either will be executed together or not at all. And while on Windows there are some APIs which you can use to do this, since we would want our string here to ideally be as platform agnostic as we can, we will include a STL library atomic, which gives us such atomic operations on an object. So std atomic int, it will make a ref count of this type. This is of course yet now a bit not longer self-contained, since our code now has a dependency on the STL. But I think for the purpose of a fast implementation of this mechanics, this is a recommended approach. So we have our reference counter, that's the important part, which knows how many objects are referring to this one instance of CX string. So first of all, when we have here our assign, then of course we will need to set this counter to 1. So m ref count. Why is it complaining? It shouldn't be complaining. Well, the IntelliSense often doesn't work properly. Yeah, it should be fine. It doesn't work properly with templates. That's one major name. So we want to store the value 1 since we have one thing referring to it. And now in our destruction routine, of course first we check whether the thing exists, and then what we need to do is we'll need to check reference count. Okay, but that's a bit annoying if we cannot use IntelliSense. Exchange. Fetch and subtract we want. Yep. So the fetch and subtract function what it will do is it will return us the value that was in the variable before the operation started. It will subtract the value that we provide from the variable, so in this case subtract 1, and it will guarantee that no other operation can kind of squeeze in between, even on a multi-threaded system when the same variables variable would be accessed at the very same time by two different threads. This is ensured using hardware instructions. So the internal implementation of these atomic operations is platform specific, so it's done differently on x86, done differently on ARM, but on pretty much any platform that is not completely trivial, it will be done with explicit hardware instructions, which also means that it will be very efficient in comparison to having to use some synchronization paradigm where we would need the operating system to do the synchronization for us. So here we check if after subtraction 1, whether before subtraction 1 the original value here was 1, because if it was 1 then we delete, and if it wasn't 1 then we just leave it as it was untouched, because the last instance, which was referring when it runs when it runs this line, will get the result that it was 1 when I told it to take 1 away, and that means that it's now 0, and that means I'm responsible for cleaning up, and it will do the cleaning up. And now what we need is we need to change this assign operation again, such that instead of doing the copying, it will actually just oh, that will be fun. We introduced a minor bug which we didn't run into, because here we cannot use no, we can here we cannot use this assign. We cannot use because it is it needs the right type, so we will need to do this here manually. Right, so the constructor from something, the constructor from a string type will now basically just do the whole shebang on its own, but our normal assign, I will quickly squirrel away this code for later. We will reuse portion of it in a minute, but this thing here will clear, and then we just say m is equals wait, let me think. We don't want to break anything. No, that should be fine. M is just equals string punct m, and now m punct m punct this fetch add 1. This will just, so we just assign the other object to our m, and we increase the counter by 1, and that's that. So this works, and now we will need to change a few other things, but we could already test whether this portion of the code works as expected. So we can create a string 1, which is from test. We will put then string 2, which is empty, string 3, which is empty. String 2 is equals string 1. String 3 is also equals string 1. And let's put this one in a scope, and then the whole thing in another scope. Put a breakpoint here. and then let's put a breakpoint on clear here. And what we will see is we will arrive at clear 3 times, and only the 3rd time we will actually do the cleanup. So let's quickly check whether this works and whether I introduced bugs. Of course I did. It's yeah, M. If you usually work with IntelliSense, it is we don't need that. Then it's easy to forget some very trivial. We already had this. Let's put that just in a scope. Then it will be fine. Okay. Wait. Why is that not complaining? Doesn't we have fetch and add? We should have fetch and add. Fetch, add. Did I write? Fetch, add. Oh yeah, I had a very embarrassing typo. Okay, so we arrive here and we just exit, so nothing happened. Then we arrive here, step over, then we check. We arrive here and we exit. So we will arrive a few more times in the cleanup, because we will have a few cases where the string was not initialized, so we will just make it clear without having any M. We arrive again. Okay, I think the next time we arrive here, we will step through everything. Yep, now we delete it. So now we kind of had 3 times the string, 3 instances of the string, but we only really created one, and they all shared the same memory for the most part, except for the most outer containing object. What now we have this fast copying method. What we are now missing is the ability to modify it and keep the data preserved, so to say, while doing so. So what we will now need is another helper function. Let's call it detach. Void detach. Okay, and that, okay, there are a few things we might need to change. We should define this as mutable, and we should define this as const. Should we? Yeah, I think we want to be able to always call detach even on a even in a const case. So let's do that. Okay, so if so how do we do detach? We first need to check whether this thing is more than 1. We need to check whether the thing is more than 1, and then we will need to decrement the counter by 1 to do so. One moment, please. I'll just look for the right sample so that this really works out correctly, because this is something that is easy to screw up the right order of operation, and then the thing doesn't quite do what it should do. Why they had that common smart array? That's a good sample. Suck. Right, yeah. So in the detach operation. Okay, well, that should be quite easy enough. So first we just really check whether m aref is greater 1. We don't do any locking at this point. And if it is greater 1, then we will need our code that we squared away earlier. So we create this, but we don't call this m, we call this or let's do differently. We'll let's call this alt m and create a new m. Length is just the length of the alt m. Size, well, it's obviously just Actually, we could optimize this way that we really cut it down just in case. Then we create a new object, then we copy everything. Alt MP data. We increase the reference count of the new one. And what we then need to do, we will need to ensure that we first clean up the old string. Clear. No, okay. Well, then we cannot do that. We need to keep this as new m. Otherwise we'll have troubles. And the new m needs to have a type. Okay. Okay, so we created a new m, we increased that by 1. Actually, we don't necessarily want to do it right now. We will use our assign function to do that, but then we would need a new copy of the assign function. We could do it later as well. So the idea is we actually don't need a copy of the old one. We can just use the actual m in this case, since we changed. That's a copy and paste bug. We replaced too much. Right. So we create a new object for now. We assign it the length of the original object. We create new memory. We copy the string from the new object. From the original object to the new object. Then we say clear, which will go through the detachment process here. What was it? Here, which should subtract this to 0. In edge cases where two threads would be doing a detach at the same time, one of them will actually arrive here and find this to be 0. So it can happen that one of the two strings will do a copy unnecessarily, but this will happen very rarely, and it should not be a major concern for us. So then we know we have a clear m, so we can assign the new m to our internal m, and then we of course increment the count of m by 1 in our detach function. And now we need to use this function. So ideally every function of our class which is not const should call detach before it does anything, because as soon as detach has been called, we know the copy of m we have is ours and we can do with it whatever we want. Before we have called detach, we don't know that. We don't have the guarantee. So let's see what we will need to work with. So the constructors are fine. The assign is assign does clear and anything, it's also fine. Append will be a problem, so append will need to detach to ensure that we can mess with m. And what else might be a problem? So let's see this. Then we have here an operator and we have a second operator. Yes, and here for example we have these two seemingly identical operators, but one of them returns a constant value while the other one returns an alterable value. And this type of operator would be often used if you would want to assign one single character in your string to a given value. So here we will always invoke detach before we return a reference to a writable character. This one is const, so we don't need detach. If we would want to use this to modify, then we would need to call detach manually, or we could also, instead of using cstring, we could take the address of whatever this one returns. Get char is const, these ones are const as well. Assign is fine. Okay, and that's it. Then now our string should be safe to modify. So here we have assigned string 2, and now we can, for example, append to string 2 test xxx, and then we'll print string 2 wait, this is char is fine. C string, and here we want to print string 3 and see that it has not been altered. Fair enough. And new line, of course. Zack. Typos everywhere. Clear is not const. But I don't think detach needs to be const. I think it will be fine if it's not const. The mutable keyword, I don't know if I mentioned that, allows you to modify so if you have a struct to which you have a const pointer, and this struct or class has a mutable member, then this member will be well, mutable. You will be able to change it with even though it was defined as const. But since we are not using this, we probably don't need that. I remember last time I implemented the function, I needed the ability to for this to be mutable, but apparently there is also a way without that. So let's see, and yeah, you see the first one was appended, the second one stayed unchanged, and of course our comparison operator still worked fine. So what we have implemented today, to summarize everything, is a very basic custom string class which provides quite nice rudimentary functionality. What would be nice to add to it would be functions to get a substring at a given offset, or sorry, to get a substring at a given offset, or insert a string in the middle of another string, or something that would find within the string something else. So these are all quite useful things. But since I already gave you so much homework, maybe that will be the homework the next time. Because I think it was already like 3 homeworks already. One day. Yeah, okay, we had one template class, one template class function, then we had here the template constructor. Were they just 2? I thought they were already 3. No, there was one in the other file as well. Yeah, here, just to get a bit more familiar with the class here. But this is very simple, so this... Actually, I gave you so much homework, you know what? We don't need that. It will be enough if you implement those 2 things. That should be enough. And it's substantially more advanced than just copying a few lines and replacing one type and one D with a I or an F or something like that. Also, the conversion here will be very funny as an optional homework. Okay, are there any questions? If there are none, then we are done for today. No questions? Okay, then I'll upload the recording and the 2 project files to the Moodle and the homework. And the next time, in the next lecture, we will take a look on pointers and smart pointers. We will implement an own smart pointer, of which type I will have to think. Maybe something trivial, maybe something not quite as trivial. And we will probably at that opportunity also take a look on STL container types. And I think next week would be a good time to assign the final project, since I think we have how many more meetings do we have? 1, 2, 3. Well, we only have 4 more lectures, so yeah, I think telling you what the final project will be next time is a good idea, so we will do that. And for the final project, you will have time until the end of the semester to implement that. Okay, so if there are no questions, then see you next week. Bye bye.